So just very briefly, the plan is that first I'll talk about linear programming, regularized linear programming. And then in the second part, later this afternoon, I'll speak about semi-definite programming. In this first context, I'll talk about two different types of regularization. So there will be 1A, 1B, 2A, and 2B. A is for log barrier regularization, and this will lead me to speak about reciprocal linear spaces. And B is entropy, so entropic regularization. And that will give rise to toric varieties. Okay, so in the semi-definite case, it's similar. So here we'll also have a log barrier part that I will not speak much about. So this is about reciprocal linear spaces of symmetric matrices. And there's also an entropic part, which will, so the manifolds here are called Gibbs manifolds. These are sometimes semi-algebraic and sometimes not, but this I'll explain. Okay, so but you are free to interrupt me at any time. I don't need to necessarily finish everything. So if something is confusing, we can go deeper into the details. Okay, so part one is linear programming. So just to remind you, this linear programming means minimizing minimizing a linear function subject to linear equality and inequality constraints. Okay, who's familiar with linear programming? Okay, most of you, good. So just to fix some notation, I'm gonna briefly recall the basics anyway. So our task is to minimize a linear function, which I'll write v dot y. Here, y will be a vector in n minus d dimensional space. The reason for n minus d will become clear. Subject to n linear constraints, which I'll write as L1y greater than or equal to 0 up to Lny greater than or equal to 0. So these Li are affine linear functions in y1 through yn minus d. Okay, so I'll assume in this discussion that these inequalities, they define a polytope of dimension n minus d. So for instance, the feasible region, it could look something like this. Okay. It's a hexagon in the plane. This is Mate's favorite polytope. Where are you? This is a permutahedron. So how many options are there for the minimizer? We'll make this a little bit interactive. Okay, so what could the minimizer be? The set of minimizers.
It could be any of the vertices?
It could be, for instance, any of the vertices. That's right. So if my v vector looks like this, and perpendicular to the v vector are the level lines of this linear functions, right? This linear function, and we're asking what's the first point of the polytope that is hit by such a level line. That will typically be a vertex. Okay. Doesn't have to be a vertex. Okay, very good. So there could be infinitely many minimizers, right? If you pick this v vector to be very special, if it aligns with the edge normal of one of my 6 edges, then the whole edge will minimize the linear function. Okay. How do you formalize this? So for each face Q of this hexagon P, in general of our feasible polytope, we can define a polyhedral cone, sigma Q. So this will be all the vectors in the dual vector space for which the minimum is attained on the face Q. Okay. So this cone parameterizes all the cost vectors V in this objective function for which Q is the set of minimizers. Here's a proposition / exercise. These cones, so these convex polyhedral cones, sigma Q, they form a complete fan in the dual vector space. The optimizers of our linear program LP prime are all the points in the unique phase Q for which V lies in the relative interior of the cone sigma Q. Are there any words in this proposition / exercise that you don't understand? Complete fan. Who knows what a complete fan is? Mate, maybe you can help us.
Yeah, a lot of it, I don't know about it, I think.
It's a section of sane cones. Okay. So it's a finite set of polyhedral cones that is closed undertaking faces and undertaking intersections. Okay, that's a fan. Complete fan means that the union of all the cones is the full space. Okay, so oh, thanks. Extra colors. Thank you. That's always good. Okay, so this fan that I'm describing here is called the normal fan of the polytope P. And so I started from a full dimensional convex polytope and I constructed a fan. This is called the normal fan of P. Can somebody draw it, Mate? This might be the normal fan of the permutahedron. Yes. With this convention, it'll be the inward pointing normal fan.
We can probably start with this, with the full dimensional cones. So. Okay, maybe I'll start with the rays because the rays will just be perfect.
That's a very good idea, yes. So we need to somehow, so the directions that are perpendicular to the edges, they need to be special in this fan, right? Because of what we just said. If you that should not matter, but you can if you want to, yeah.
Should get the rays perpendicular to the faces. Right?
Exactly.
And now, so if this is maybe this edge is E, then this ray should be the cone sigma E.
Perfect. Well, almost, because we're inward pointing. Okay, different people have different conventions. I like when the rays point into the polytope. Okay, so the ray corresponding to this edge is the one that points in this direction. Okay.
And then these full dimensional cones should be sigmas of vertices.
Perfect, thank you. Yes, so for instance, in the example that I gave, so this vector here, this vector V, in Mate's picture, it lies here. So it lies in the relative interior of this cone, and that cone corresponds to this vertex. So this is V, this cone is sigma V. Okay, so this is the combinatorial solution to a linear program. And so in a perfect world, to solve a linear program, you just compute the normal fan of the feasible polytope, and you can see which face is the optimizer. But that's of course very expensive for larger programs. Okay. Right. So in particular, the solution. So if as long as V is not zero, the optimizer or all optimizers, they lie on the boundary of the polytope. And so it's usually there's a unique optimizer, which is a vertex. This is something we already observed. So as long as you pick a V inside one of Mate's two-dimensional cones, the optimizer is a vertex. If you pick it very special to lie on one of these rays, it'll be an edge. Okay. So now I'll switch to the regularized setting. So this is just standard unregularized linear programming. And now I'll slowly move towards regularized linear programming. But for that, I'll write a linear program in a so-called standard form. So you can always write the linear program as follows. So we minimize w.x subject to the equality constraints ax equals b, and x is non-negative. Okay, so what I've done is I've taken this polytope, I've taken this hexagon, and I've written it as a linear section of the positive orthant in R6. Okay, that's how you pass to a linear program in standard form. I'll write standard form. Okay, couple of words on these parameters. So A will be matrix of size D times N, and I'll write the columns as A1 through AN. I will assume, so I can assume without loss of generality that this has rank, that this has full rank. Okay. None of the columns is 0. If one of the columns is 0, then the feasible set is not compact, which is something I'll exclude. And if we want this feasible region to be non-empty, then B better lie in the cone that is generated by the columns of A. Right, so this is saying there exists a non-negative vector X that combines the columns of A to make B. Okay, so B must lie in the conical hull of the columns of A. Okay. So this, sorry, I wanted to, so I said that I want this feasible region to be bounded, and it's sufficient to assume that the entries of my A matrix are non-negative. Okay, you can think about this. So now with these assumptions, this makes a bounded convex polytope. Okay, so this ensures feasible polytope is bounded. How many facets does this polytope have? bounded and non-empty. How many facets do you expect polytope would have? D, I don't agree. Could have D facets. More like N, right? So I have N in, sorry, minimize is now X is in Rn, sorry. Okay, because it gets, so A is a D times N matrix, so X has N entries, so I'm minimizing over Rn. So there are N inequalities. So you could expect that each of these inequalities makes one facet. That is not necessarily so. It depends a bit on B, but our polytope could have at most N facets. Okay. Do you agree, Eunice, or? Okay, so at most N facets, because I'm writing down N inequalities, okay? It could have less than N facets. Mateusz is squinting his eyes. Okay, good.
In the example, there are fixed.
That's right. So this was not in standard form. So here I'm assuming I am optimizing over a full dimensional polytope in our N minus D. Now I change coordinates so that the polytope is represented as a slice of the positive orthant. So here I would pass to, in fact, we'll do it later in an example. So here we will have N equals 6 and D equal 4. So the matrix A will be a 4 times 6 matrix. More questions? Okay. So what's regularization? So the picture that belongs to this linear program is still this, right? Now you need to think of this picture as happening in a two-dimensional affine space in R6. Right, and the intersection of that two-dimensional affine space with the positive orthant is our hexagon. Draw the old picture again. That's this linear program. Now, what is regularized linear programming? So in the regularization, I'm just gonna change the objective function a little bit. So I'm gonna, instead of minimizing w dot x, I'm gonna minimize w dot x plus a strictly convex function. Okay, so I'm gonna add epsilon times some convex function h, and I'm gonna keep the same feasible polytope. Okay, so epsilon is called the regularization parameter. So if you drive epsilon to 0, you're back to the old linear program that you originally wanted to solve. Right? So this is regularization parameter. And h is the regularization function or the barrier function. It's usually in convex optimization, this is called the barrier function. And it is strictly convex on the positive orthant. Strictly convex function on Rn non-negative. So if it's strictly convex on the positive orthant, it'll be strictly convex on any affine slice of the positive orthant, right? So it's also, it restricts to a strictly convex function on our feasible polytope. Okay, what does this do to the picture? So here we had an optimal vertex, which is the first point of the polytope hit by the level lines of this linear function. Now we're getting a very different picture. So now, because we add this strictly convex function to the objective function, we're going to get level lines that look a bit like this. We're going to have a minimizer that lies in the interior of the polytope. Oh, sorry. I'm sorry, I want to move it up. But so now the minimizer lies in the interior of the hexagon. Okay. And if epsilon is small, you can expect that it still lies near the optimal vertex. Okay. So I'm going to add a couple of things to this picture. This is for a fixed small positive value of epsilon, okay? We said if epsilon goes to 0, we recover our old optimizer. So I'm going to call this x star of epsilon. This here is the x star of 0. And an interesting thing you can do is you can drive epsilon to infinity and just minimize the barrier function on the polytope. This will give you a preferred interior point of the polytope that minimizes this convex function. Okay, so there's a point x of infinity, x star of infinity. That is some preferred center of our barrier function. And as epsilon moves over the positive real numbers, this optimizer describes a path that travels through the polytope all the way to the optimal vertex. Okay.
Then what would happen if the linear program was optimized on a whole edge?
That's a very good question. So then, I mean, I usually exclude this, but I would expect that the path lands somewhere on the edge. And where it lands on the edge, that depends on how you choose the age function.
Again, the assumption on the barrier function.
There are assumptions on the barrier function, and in a second, I will make a choice. I will give a formula for H. So the usual assumption is, for instance, that it goes to infinity on the boundary of the region. That's typically what you want for a barrier, and that ensures that there is a unique minimum in the interior. And I think if it diverges fast enough, then convex optimization algorithms, they converge fast to this minimum. Okay. Where was I? Okay, so this philosophy of you first compute the optimizer of the regularized program, and then you drive epsilon to 0. That's the philosophy of interior point methods. And this is the motivation interior point methods. That's the motivation for my talk. Okay. So first step is solve the regularized linear program, by which I mean this, RLP. You can solve it for finite epsilon or even for epsilon infinity. Start at the center, x star of infinity, and then drive epsilon to 0 and follow the optimizer using some continuation procedure. Okay. So this is the motivation. Now, I won't talk much about how you do this in practice, but what I'll be interested in is the geometry of this picture. So it turns out that for some natural and popular choices of H, the story is algebraic. So for some choices of H, so what do I mean by that? So this path, this green path, the optimal path, is actually a segment of an algebraic curve. Segment of an algebraic curve. And the and the optimizer, so x star of epsilon, is the unique positive solution to a system of polynomial equations. Okay, so that's the story that I want to tell for a couple of choices of H. I'll tell you what the polynomial equations are, what are the varieties involved. All right. That's the general motivations. Are there questions about this? I guess that will follow from convexity. So we'll find this point by imposing first order optimality conditions, and there are no other critical points inside the polytope. But yeah, so case by case, you can call it a theorem. Right. So from these data, I don't need to worry about computing the normal fan of my polytope. Sorry, I just need to. I know that now the objective function is convex, so I can just like pick a starting point here and do some convex optimization to find x star of epsilon. Right? I don't need to do any combinatorial computations. Very good question. Who knows the answer? I mean, the answer is no. Who knows why? It's singular, right? So you have like a linear function on a polytope, and the optimizer is going to be on the boundary. So there is no, you need to really take the boundary equations into account in that case. So in this case, you're safe because the optimizer lies in the interior, and you can really just wait until the Hessian is 0. If you don't have the regularizer, you can't do that. And of course, for the numerically oriented, if epsilon goes to 0, it gets more and more singular. Gets harder and harder to find that interior optimizer. Okay, so that brings me to 1a, which is about logarithmic barrier for linear programming. And here I will essentially summarize for you some results from a paper by Jesus de Loera, Sturmfels, and Cynthia Vincent. Papers from 2010. Okay, so a while ago. But I think this is, yeah, this, I found it natural to include this story. So we're gonna choose for our H function, we're gonna choose the logarithm. Minimize w dot x. And here is the convex function. I'm gonna take a sum of each coordinate. I take the logarithm. It is very natural choice. It goes to infinity on the boundary, and it is strictly convex on the positive real line. Called the logarithmic barrier function. Constraints are the same. So let's compute the optimizer here by imposing first order optimality condition. So maybe you remember from your previous life something called Lagrange multipliers, optimality conditions. So I need to compute the gradient of a Lagrangian function. So to construct a Lagrangian, I write down the objective function. And then I subtract lambda j times the jth equality constraint, right? I'm going to use the shorthand notation. I'm going to make a vector of Lagrange multipliers called lambda. And what I need to subtract is lambda transpose times my linear constraints. Does that confuse anybody? So lambda is lambda 1 through lambda d. Each lambda I multiplies one row of ax minus b. Okay. Gradient of this needs to be 0. Okay. So that means if you write this out, so the derivatives with respect to x, they give me the following condition. So epsilon over x, or how should I write this? Maybe write it fully. So epsilon over x1, epsilon over x2, dot, 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 epsilon over xn is equal to W transpose minus lambda transpose A. These are the x derivatives. Okay. The lambda derivatives are easy. Let this sink in while I erase. Okay, so if we solve this for fixed epsilon, for fixed positive epsilon, so it is, okay, but I want to eliminate lambda from the equations, right? So if I eliminate lambda from these equations, then I see that the reciprocal of x lies in the affine space that is the row span of A plus W over epsilon. So I take the reciprocal of x. This lies in the affine space. It's a d-dimensional affine space. You take the row span of A, add the point W over epsilon. Okay. Another way of saying this is that x lies in the reciprocal affine space given by these data. Okay, we'll come back to this. Now you see if epsilon goes to infinity, then the reciprocal of x just lies in the row span of A. Epsilon goes, sorry, thank you. That's right, epsilon goes to infinity. Then our center, so this preferred interior point, is the unique positive point in our hexagon that also lies on the reciprocal of the row span of A. Okay. Now, for any epsilon, so if we want to maybe think about what could be the defining equation of this green path. So if I also try to eliminate epsilon from the equation, then you see that for any epsilon, this reciprocal point will lie in the row span of A, but you add the vector W transpose to the row span. And I will call this matrix, this is an augmented matrix with D plus 1 rows and n columns. I'll call it A hat. Okay. Okay, because, so I can always, exactly. So if I want to eliminate epsilon 2, I can always, if the reciprocal of x lies in the row span of W transpose and A, then I can choose epsilon so that the coefficient standing with W is 1. Okay. That's the reasoning behind this. Okay. So we have three slightly different scenarios. The first one is to compute a point somewhere in the middle of the path. The second one tells you how to compute the center, x star infinity. And the last thing tells you how to get equations for the green curve. So motivated by this, I'm going to introduce some family of varieties. We're going to do an example in a second. So I'm going to associate a variety to a matrix. So the reciprocal linear space denoted R sub A for reciprocal of a matrix A. And this could in general be a complex matrix, is defined as the Zariski closure of the following set. So I take all points, the reciprocal of all points in the row span. I need to be a little bit careful because I can only take points that I can actually invert, right? So I can take points in the row span that lie in the torus. Any of this unfamiliar? Anybody, do you know what the torus is? Okay. Tell me if you don't, okay? So this is just, I'm saying I take points in the row span, but I forget about the points that have one or more coordinates equal to 0, because then I can't invert. Okay. Dimension. Anybody? Enrica. Dimension. The eyes are like. So let's think about it. Is there a way to parameterize this? You think of a way to parameterize it. What would be the dimension of this variety?
It won't be the dimension of A unless it's the empty set.
I see. Okay. Yeah. Okay. So A has no 0 columns. Okay, so let's assume it's not the empty set. But yes, okay, so it's the same as the dimension of the row span of A. So you take basically any point in the row span and you send it uniquely to a point on this variety. Okay, so it's the rank of A. The dimension of this thing is the rank of A. Okay, that's part of the theorem I'm going to write. So this reciprocal linear space is irreducible of dimension rank A. Its degree is something called the Möbius number of A. So this is the Möbius number of the matroid represented by A. That's of course non-trivial. And the ideal, the vanishing ideal. Who knows what a vanishing ideal is? Vanishing ideal is the ideal in the polynomial ring consisting of all polynomials that vanish on every point of our variety. Okay? So that's my notation for the vanishing ideal. I of Ra, this has a universal Grubner basis. Indexed by the circuits of the matroid. Okay, so these are maybe some heavy words, but we'll do an example and I'll explain these words to you by means of an example, okay? Message is these varieties are very well understood, okay? And they have a very, very combinatorial flavor. All the invariants only depend on the matroid that A represents. That means if you take another matrix A with the property that, so it has the same subsets of D columns whose determinants are non-zero, you'll get the same invariance. Okay, so it only depends, the invariance of this variety only depend on which D by D submatrices are invertible. Okay. I should say, so this is this theorem is not by these people. This goes back to Proudfoot and Spire. They have a very nice, very influential paper in which they study these varieties and their degenerations. Yeah. I haven't thought about this. My intuition is no. I think you always miss something. Yeah, yes, sorry, yes, because no, okay, maybe I should be careful with what I say. I believe not. I believe you always miss something in this case. It's not like so in the toric case, there's you can, yeah.
So you take this set of inverses intersected with the torus, and then you take the closure. But probably my intuition is completely wrong, but it seems that when you take the closure, you recovered everything that you lost when you made the intersection.
But there's also stuff at infinity, right? That you could.
So you take the closure in the affine space. I mean, if you take the closure in the affine space, I think you could give an example. Like if the original row span is just a single line that doesn't meet it's not containing in any coordinate space. Then the only thing you lost when is first is the origin, but the origin seems to be compared to the origin again. So then if you take program with a hundred,
so whatever you get before taking the closure is isomorphic to the hyperplane complement given by the columns of A. And I don't know if maybe Mateusz knows if there's an example where you can embed this as a closed affine variety. So the question is, does it ever happen that you don't need to take the closure? So you take the reciprocal of all the non-zero points, and that's already closed inside an affine space? I think not. Or that would be a very boring example. Like a point, okay. Like a point. Okay. Example. Okay, so here's a running example I want to use in the rest of this lecture. So minimize the following linear function. Six decision variables. Subject to. AX equals B. And of course, X is greater than 0. Okay, so you can solve this during the coffee break. Okay, find the actual optimizer during the coffee break. So, but we can talk about the regularized version of this. First of all, what's the polytope? What do you think the polytope is?
Yeah.
A square?
Somehow like a square, but like this. Oh, but I guess all conditions, right? And we like this It's probably close because you said it's not close. Okay.
There are 6 conditions. Six inequalities. It's a hexagon. Okay. So we're taking 4 conditions on 6 space. And we're imposing 6 inequalities. So this is a hexagon in a plane. Okay, so an example of a circuit of this matroid. So a circuit of a matroid is a minimal dependent set. So I take a subset of the columns that is linearly dependent, and it's minimal with that property. So if I take out one of them, they become independent. Okay. So an example of a circuit of this matroid is 1, 2, 4, 5. So take columns 1, 2, 4, and 5. That makes a matrix with dependent columns. And if you remove any of the columns, it becomes independent. Okay. This is a circuit. And such a circuit by this theorem gives me an element of a Grubner basis. So let's find the equation that corresponds to this circuit. This being a circuit implies that there is a unique linear relation between these columns. Okay, so what's the relation? You can check that A1 minus A2 minus A4 plus A5 is 0. Okay, that means every point X that lies in the row span of this matrix satisfies X1 plus minus X2 minus X4 plus X5 is equal to 0. Okay, stop me if it's not clear. Any point in the row span satisfies this linear equation. But I'm interested in the reciprocal, okay? So if you're in the reciprocal of the row span, then you satisfy X1 inverse minus X2 inverse minus X4 inverse minus X5 inverse is equal to 0. This is an equation that is satisfied on the reciprocal linear space of A for every point with non-zero coordinates. Thank you. And now you clear denominators. Okay, so to find a polynomial equation vanishing on the reciprocal, we clear denominators, we find a cubic equation. That is contained in the vanishing ideal of our reciprocal linear space. Okay, now the theorem says, so this is to check that this vanishes on the reciprocal linear space is easy. Okay. The non-trivial thing is that if the theorem says if you run over all circuits, compute this generator for all the circuits, you get not only a set of generators of the ideal, you get a universal Grubner basis, which means that it's a Grubner basis for any monomial order you pick. Okay, so very nice combinatorics. There are 2 more circuits, so you can check this using your favorite software. The other one is 1, 3, 4, 6 and 2, 3, 5, 6. Okay, so about the degree. I told you the degree is a Möbius invariant. I should say this in a slightly more geometric way. So I'll give away here that the Möbius invariant is 7. And there are a couple of ways to compute this. So let's see. So a geometric way to think of this Möbius invariant is as follows. You compute a generic affine translate of the kernel of A. This is linear algebra, okay, but I'll tell you, I computed this yesterday, so you can parameterize this generic linear translate, generic affine translate as follows. Okay, so I have a 2-dimensional affine space, and it has this linear parameterization. Okay, linear algebra. Okay, How do you get the Möbius invariant? Well, you draw this arrangement of lines for generic values of z. So here I have two lines that are parallel to the y-axis, two lines that are parallel to the x-axis, and then two that have this angle. So the arrangement will look something like this. Okay, and every time you try to draw something generic, it's not generic, you have to pay attention, right? So that's the picture. And now you count the number of bounded chambers. Am I missing one? That's 7. Okay. So that number is constant for generic z, and it counts the Möbius invariant. Another way to do this, if you're into matroids, so you can compute the characteristic polynomial of the matroid. That means for every subset of the columns, okay, what you do is you take any subset, then it's -1 to the cardinality of that subset, variable q raised to the power co-rank of your subset of columns. Is that the same thing? That's the characteristic polynomial, same as chromatic. Okay. So this is a polynomial of q. Now you evaluate this at q equals 0 and take the absolute value. Gives the number 7, gives the Möbius invariant. Okay. Yes.
Why the corresponds construction that?
Oh, the y is not so easy. I'm just explaining to you, I'm giving you a geometric definition of the Möbius invariant. I'm not going to prove this theorem, that we don't have enough time. Yes, so I'm giving you one way to define the Möbius invariant. Okay, so you parameterize a generic affine translate of the kernel. You draw the corresponding arrangement of hyperplanes, and you count the bounded regions in the complement. Okay, so this divides up R2 into polyhedra, some of them bounded, 7 of them bounded, others unbounded. You only count the bounded ones. Okay. Okay, so the analytic center is a name for the point x star of infinity. Let me give you some terminology introduced in this De Lovera, Sturmfels, Vincent paper. X star of infinity is called the analytic center of the polytope. Okay, I should almost move on to toric variety, so I'll say in words. So the analytic center of the polytope is the unique positive solution to the equations x lies in the reciprocal and x is non-negative. And x lies in the polytope, right? Okay, so you can put these we'll put these equations in Oscar in a second, okay? You can solve these equations over the complex numbers. There will be precisely one solution with positive coordinates. That's your analytic center. Okay, because there is precisely one point that satisfies first order optimality conditions on the polytope. So these are equations for the analytic center of P. So how do you compute? So another piece of terminology. So the green path, so the path x star epsilon for epsilon positive is called the central path, and its closure, so its Zariski closure is the central curve. And the paper I'm citing is titled The Central Curve in Linear Programming. But how do you compute that? Well, so here we need that X lies in the reciprocal of this extended matrix. And so the equations for the central curve are given by X lies in RA hat and AX equals B. This is one that this defines finitely many points, right? If everything is sufficiently generic, one of which is the analytic center. This is one dimension higher because the row span of A hat has dimension one more than the row span of A. So this actually defines a curve. And the claim is that for generic B, it's proved in this paper, for generic B, this curve is the Zariski closure of the central path. These are equations for the green curve. Okay, should I show you this very quickly in Julia? Oh, I should do something here. How is this? Larger? Okay, good. I see thumbs up. All right, so this utils package is just something, I wrote to make my life a little bit easier. Okay, so the first 4 lines, I'm just defining everybody. These are A, W, B, and A hat from my running example on the right whiteboard. Okay. Okay, central sheet is another piece of terminology. Central sheet is this thing. Okay, so we're computing R A hat first. Okay, I make a matroid and I compute the circuits. This matroid has 1 circuit. So you should follow in the terminal here, right? Okay, so the unique circuit of this matroid is 1, 2, 4, 5. And that gives this defining equation for the central sheet. So in our example, the central sheet RA hat is a hypersurface. It's a cubic hypersurface in 6-dimensional affine space with 1. Okay. So it turns out that if you add this vector W, the vector W is 3, 5, 7, and so on. You add that to this matrix, then the columns still satisfy this relation. Okay. So this thing remains a circuit. So the central sheet is a cubic hypersurface. I can compute the ideal to confirm this, right? So if you compute the defining ideal of this reciprocal linear space, you get the same cubic equation that I wrote down on the whiteboard. You can compute the degree, it's 3. And we can see the number 3 from the characteristic polynomial. It's the absolute value of the constant coefficient of the characteristic polynomial. Okay, Möbius invariant. I chose prime numbers because I like prime numbers, and it really came out by accident like this. It's if you pick other things, then of course. No, this is completely made up. Okay. Okay, so now let's do the slightly more interesting one, the one that we started doing on the whiteboard. If you start from the matrix A, you get a rank 4 matroid. It has 3 circuits, as I told you. These are the ones that I wrote down. Consistently, the ideal is generated by 3 cubic polynomials. One of them, the one we wrote down. The degree is 7. Characteristic polynomial is this. The constant coefficient is 7. And okay, this is the null space of A that I use to compute this parametrization. Okay, now let's compute the analytic center. So I define the ideal, I define this ideal. Okay, so I take the ideal of RA plus the linear ideal generated by AX minus B. And then in Oscar, you can just solve it. So that you can do real solutions is the command. And it spits out a big output. Let me show you. Okay, so the first part of the output contains the actual solutions. How do I make this better? Okay, maybe this is a bit, yeah, it's a bit hard. So these are rational approximations to the solutions. That's what the algorithm in Oscar does. Okay. There are 7 solutions in total over the complex numbers, but all of them are real. That's no coincidence, that's a theorem. Okay. All of them will be real and precisely one of them will be positive. So I can tell you which one it is, but I don't know if it's very informative. Maybe you have to believe me. Yeah, this one looks positive. Okay, all of the others have a minus sign somewhere. So this and the one that I made blue is the analytic center of our hexagon. Okay, very good.
Name here in the center, you're going to take this variety, RA, effective the variety generated by equations, right?
Linear equations, yes.
And also want to say positivity.
Exactly, yes. So this we basically computed here, right? So for the analytic center, the optimality conditions is X inverse lies in the row span of A, but there's also the condition that X lies in our polytope, right? So AX equals B and X is non-negative. Okay, so if I look at just the equations, I ignore the inequalities X greater than 0. This I can solve in Julia. Okay, I find 7 solutions. Because I take a variety, I intersect it with something linear, you expect degree many solutions. The degree is 7. Out of these 7, only 1 satisfies also the inequality constraints. And that's because we have a convex optimization problem. There's only one minimizer inside the polytope. Because the row span of A hat has dimension 1 more. I added a row to A. I added the vector W. Okay, and the dimension of the reciprocal is the same as the dimension of the row span. More questions? Okay, then let's go to 1B. Okay, I lost my slides. Did I close it? Okay. I only need to show 1 slide before the break, so it doesn't really matter, but let's put it up. Okay, so now I'm gonna choose a different regularization function and the story will be very similar, except we're gonna need to consider a different kind of varieties. Okay, this is called entropic regularization. Okay, so this is from a paper with Sturmfels. There is François-Xavier Vialard and Max von Renesse. Okay, this time we minimize w dot x minus the entropy. So that's plus epsilon times I equals 1 through n, xi log xi minus xi. So it's like a slightly funky version of the entropy functions. I need the minus xi to make everything work. Subject to the same constraints. X is in, well, okay. X is in Rn, but the logarithm of a negative number. So X is in Rn plus. Okay, so for this section, it will be nice to assume that A and W are rational numbers. Okay, first order optimality conditions. We'll start out exactly like we did before. So on a side note, this function is strictly convex on the positive orthant, like we need. It's not a barrier function in the usual sense. It is not, the limit for x going to 0 is not infinity. Okay, this actually, the limit for x going to 0 is 0, but the derivative is infinite at x equals 0. And it turns out that that's enough to have a unique minimizer on the interior. Okay, if you're interested in this, think about it. But okay, so I'm claiming this function works for interior point methods. First order optimality, the Lagrangian this time sum of xi log xi minus lambda transpose ax minus b. Gradient is equal to 0. This tells you that epsilon, so the derivative, I missed something. The derivative of this function is just a logarithm. That's why we chose it in this way. So you compute the derivatives, you find that epsilon times the logarithm of x is lambda transpose A minus W transpose. Okay, so now you see that the logarithm of x, epsilon times the logarithm of x lands in this affine space. And of course, the derivatives with respect to the Lagrange multipliers, lambda, they enforce that AX is equal to B. So for fixed epsilon, fixed positive epsilon, we are saying that log of x lies in the affine space rho of A plus W over epsilon minus. Okay, using the same reasoning as before. So we're saying x lies in the exponential of an affine space. Epsilon to infinity says log of x lies in rho of A and any epsilon, so to compute the optimal path, we have that log of x lies in rho of A hat. Okay, so what are the relevant varieties? I gave it away in the beginning. Definition. the toric variety or affine toric variety of a matrix A is the closure, the Zariski closure of the exponential of its row span. Yeah. You take the Zariski closure and C to the n of the exponential of every point in the row span. Okay, who has heard about toric varieties before? Good. So Mateusz writes in his book that the world is toric. So if you like entropic regularization, then your world is indeed toric. Yeah, Otto.
You define a map that goes from the variables essentially to the variables exponentiated by multi-digits, right? Is this recoverable from this definition or?
Absolutely, good question. How do you do that?
It's separable.
It's just a change of parameters, right? You just map t to the exponential of t, and then you apply the monomial map. Okay, so this is a different way of thinking. So if you're used to thinking about toric varieties as being parameterized by Laurent monomials, that's fine too. That's an equally good definition, but I'm claiming it's the same thing. It's just taking a linear space defined over Q and applying the exponential. Okay, I'll let this, well, maybe, okay, I can clarify during the break if this is not clear to you. Yeah, so I'm claiming that this is a algebraic variety. So what are the properties? Well, Otto, maybe you can tell me the dimension. Very good. It's the rank of the matrix A. Reducible, irreducible. Irreducible. Why A is irreducible of dimension rank A. Degree. The degree, okay, so this you'll have to take with a grain of salt. So I'm going to write it's the volume of the convex hull of the columns of A append 0. Okay, so 0 union A means you take all the points in A, you plot them in D-dimensional space. You also plot the origin, and then you take the convex hull. That gives you a polytope. And I'm writing that the normalized volume of this polytope is the degree of the toric variety. And for this, we need a couple of assumptions. So here I'm assuming that A has integer entries, which you can always make true without changing the row span. Right? Just clear denominators. And I'm assuming that A has no lattice index. This is a technical assumption, but morally, so the degree of this toric variety you can compute from the volume of this polytope. We'll do an example. Maybe I write a red star here. So this is under some assumptions. That's a theorem by Kushnirenko from the 70s. And the ideal, so for the reciprocal linear space, we also discussed the ideal. So the ideal of this affine toric variety is generated by binomials. It goes, so the generators go x to the u minus x to the v, where u and v range over all non-negative integer vectors for which u minus v lies in the kernel of A. Okay. So also, oh, I didn't write it. Sorry, thank you. The toric variety YA of the matrix A. Thank you. Yes. It's not restrictive at all. You can always start from a matrix and make it have no lattice index and still give you the same toric variety. I expect so. I mean, you can get rid of the lattice index by computing a Smith normal form and basically setting the invariant vectors to 1. Yeah, we can do an example to clarify what I mean by the second assumption, but let's do that offline. Okay. In our example, oh, it's still there. Good. I don't write it again. So for our A matrix, what's the toric variety? Anybody with a trained toric eye understand what the toric variety of this 4 times 6 matrix is? These are the rank 1 matrices of size 2 by 3. Okay. This is clearer from the monomial parametrization than from the exponential definition, right? Yeah, okay. So the ideal, the binomial ideal, is generated by the 2 by 2 minors of x1, x2, x3, x4, x5, x6, so as to impose that this matrix is rank 1. And the polytope, so the convex hull of 0 union A, is a pyramid over a 3-dimensional polytope. So if you take the convex hull of A, that will be a 3-dimensional polytope because all the lattice points of A are contained in the hyperplane where the sum of these two coordinates is 1. Okay, so these points that you plot them in R4, but they actually lie on a 3-dimensional affine space. So you take the convex hull, you get a 3-dimensional polytope. And then you add the origin, so you get a pyramid over this 3-dimensional polytope. And the 3-dimensional polytope is a Toblerone. What's the volume? So the volume of the pyramid is going to be the same as the volume of this thing. So this is half of the unit cube, so it'll have Euclidean volume 1/2. But when I say normalized volume, I mean you multiply with dimension factorial. Okay, so the degree of this thing is 3. That's the degree of the variety of rank 1, 2 by 3 matrices. Okay. Bit of terminology. We have, okay, 8 minutes. So previously we had the analytic center in the log barrier regularization. So if you use entropic regularization, we call this point the Birch point. This is after a theorem called Birch's theorem in algebraic statistics. It's just a name. So this is the unique. In our example, the Birch point is going to be the unique positive rank 1 2x3 matrix satisfying the linear constraints because of this, right? So if you are the optimizer for epsilon going to infinity, then you lie on the toric variety of A, means you're a rank 1 2x3 matrix, and you satisfy the linear conditions AX equals B, and you're non-negative. And that nails it down to the unique minimizer. This is called Birch point. There is a sheet. So previously we had the analytic sheet. We can here define the entropic sheet as the toric variety of A hat. This is a degree 2 hypersurface. Again, also because I chose a lucky list of prime numbers, it has a very easy binomial equation. And this sheet, of course, contains our previous toric variety because the row span of A is contained in the row span of A hat. Entropic sheet. What else? So the path is called the entropic path. And the Zariski closure we call the entropic curve. This is an algebraic curve given by the equations in our example. So you take the equation of the entropic sheet and you add the linear equations. Just like before, but with reciprocal linear spaces replaced by toric varieties. Yeah, so this is maybe the moment to show you the slides and then we can take a break. Questions? Mm-hmm.
So, kind of getting that makes so do you get this Y area variety determinant?
In this case, yes. In general, no. So if you take any matrix size, D1 times D2 matrices of rank 1, you get the equations from the 2x2 minors of a generic matrix. Right? There are some other cases like the rational normal scroll is a toric variety that you can write as the 2x2 minors of a matrix with, but it's not a completely generic matrix. There are some cases in which you can express it as a determinantal ideal, not in general. Mm-hmm. That I can believe, yes. So I'm saying here you're going to need all three of them. Yeah, in general, there is a way to compute a basis for the toric ideal that uses Markov basis. I think this Bern's book is a good reference. Grubner basis and convex polytopes. In general, so one thing you can do is you can compute for each kernel vector of A. So you compute an integer vector in the kernel of A that will allow you to make a binomial that vanishes on the toric variety, right? So you can do this for a Z basis of the kernel. That will give you n minus d equations, which in general do not generate the ideal. If you take the ideal generated by these n minus d equations and you saturate it by the product of the variables, then you get the toric ideal. Saturation is a Grobner basis procedure, and I'll give you, this algorithm will return you a Grobner basis for the toric ideal. It's a naive algorithm, but it works. Anything else? Okay, so computing toric ideals, of course, in general can be arbitrarily hard, but it's comparatively easy compared to other rational varieties. They are easy to implicitize. Okay, good. Then let me show you one slide. So the project I had in mind for tomorrow is related to this slide. So one reason why people like this entropic regularization is that there exists an iterative algorithm to compute x star of epsilon, okay? So usually the equations that we would write down as computational algebraic geometers is, okay, we write the equations for the toric variety and ax equals b, right? Then you compute, our methods compute all complex solutions, and then afterwards we go look which one is positive. That's one way to do it. It's not desirable because you compute many solutions that you're not interested in. And this is really one of the magic cases in which you can really design an efficient algorithm that computes only the positive solution. And it's an iterative algorithm, and it knows about this geometry. Okay, so what this iterative proportional scaling does, I have 2 minutes left, so I cannot explain the algorithm. But what it does is it starts somewhere on the toric. This picture is, the blue curve is the toric variety, okay? And it intersects the green feasible polytope P in precisely 1 point. That's x star of epsilon, or x star of infinity, okay? You start somewhere on the toric variety, and throughout the iteration, you stay on the toric variety. So this is, of course, this is an algorithm from the 70s, and it's not explained in this way in that paper. But if you look at it, it's true. So the algorithm iterates on the toric variety, and it converges to the unique intersection point with the triangle when the iterations go to infinity. That's very different from a usual convex optimization. Well, if you would do the convex optimization approach, that means you start somewhere in the triangle, and you stay in the triangle all the time until you converge to the intersection point with the blue curve. That's geometrically a very different thing to do, right? So I'm claiming this iterative proportional scaling algorithm with whoever wants to do this project can study this algorithm a little bit, and it knows about this toric geometry that I've explained. B, the triangle is given by ax equals b. Look, so the map A maps the triangle to B, right? So the points in the triangle are the points x satisfying ax equals b, and they are non-negative because they are in the simplex. It's a cartoon. Okay.
And this parameter simplex is.
It's a cartoon for the non-negative points. So if you want, you can imagine that one of the linear constraints is that the sum of the coordinates is 5. So the non-negative points whose coordinate sum is 5, they make a simplex in Rn, okay? So the green points are the non-negative points satisfying ax equals b, so the green triangle is the feasible polytope. More questions? 1 minute over time.
It's my role to ask if.
All right.
Very efficiently. How would this compare to like running a serial point?
That depends. I don't know. I cannot confidently answer this question. But it's really used. So this is known in our example case, this is known as sinkhorn scaling. Sinkhorn the Sinkhorn algorithm, I guess. Somebody familiar with that? Yeah, so in the case where the toric variety is a product of two projective spaces, this is Sinkhorn scaling. In the general case, it's called iterative proportional scaling.
The plan you also mentioned something, yes, entropy, but also gives money.
That will be semi-definite programming after the break. Yeah.
Next
round.
But maybe other question. So I have maybe a philosophical question, because I enjoyed a lot your exposition. If it seems you try to make a parallel between the reciprocal linear of a matrix in the previous slide, let's call this slides, and now the toric variety, is exactly. I'm not sure if I understood correctly, or it was really the message you wanted to, because I never made this parallel and.
Yeah. So it's I mean they're similar and different, of course. So the reciprocal linear space really arises from this logarithmic barrier, and the toric variety arises from the entropic barrier, the entropic regularization problem. And the analogy is that they're both highly combinatorial in flavor, these varieties, but in the reciprocal story, the combinatorics is governed by matroids. And in the toric story, the combinatorics is polytopes. Right? So these are two families of varieties that are like super popular in algebraic combinatorics, and they pop up just from different regularization functions. Very similarly in algebraic statistics, the reciprocal linear spaces, they pop up for the maximum likelihood estimation for linear models. And there's also something called exponential families, and there you solve equations on toric varieties. So it's true that they seem very different, but they show up in similar contexts, yes.
There are no other questions. Thanks, Stephen.